All right, welcome to Lecture 13, Part B. Now, in Lecture 13, Part B, we're going to learn about a new term, and it's really just a different way of writing a formula. So there's two kinds of formulas, really, molecular formulas and empirical formulas, and we're going to talk about what the difference is. After that, we're going to move on in Part C to do a little calculation that has to do with these terms. So that calculation also involves our good old friend, the mole. All right, let's go ahead and flip over and get started in this lecture. Okay, so what's the difference between a molecular formula and an empirical formula? All right, well, a molecular formula is going to be a formula that shows you the actual number of atoms in a molecule. So if we could see the molecule, how many atoms would be in this thing? All right, that's called the molecular formula. Now, the empirical formula is just the lowest ratio of atoms in a molecule. So it's kind of like we've simplified the formula. We've simplified it or reduced it. That might be the way they say it in math class, all right? So as far as another thing that kind of is different, or I should tell you about them, is that so far, really, this semester, we've generally been using molecular formulas. We have been using molecular formulas. All right, we have been using these so far. So why do we even want this other way of writing the formula of a compound? Why do we even want empirical formulas? Well, the reason is that it turns out empirical formulas are way easier. They're easier to determine in a lab. We'll say in an experiment. So we're going to learn about kind of how you determine the empirical formula. And, oh, that's a little messy there. Let's rewrite that. How you determine the empirical formula of a compound. And really what we're going to hear about is the calculation that goes along with it. All right, so before we get to any of that, let's just kind of do a few examples. Molecular formula versus empirical formula. Again, actual number of atoms in a molecule compared to the lowest ratio of atoms in a molecule. So an example would be something like hydrogen peroxide. Hydrogen peroxide, if you could see it, this is what you would see right here. This is what a hydrogen peroxide molecule looks like. It's two red guys, like the red guys are your oxygen, and it's hooked up with two white guys. The white guys are your hydrogen. So we always use those colors for these atoms. So two reds, two oxygens with two whites, two hydrogens. So I got a little model of it in my hand, or you can look at it on the screen. So all put together, there's 4 atoms in this thing, right? 2 oxygens, 2 hydrogens. So the formula, H2O2, that's the molecular formula. You're telling me how many of each are really around, the actual amount. But if you notice, both of those numbers are divisible by 2. We could divide them both by 2. And when we reduce down the formula and use the smallest numbers you could just to tell me the ratio, that's what an empirical formula is. So the empirical formula of this thing would just be HO. So another way of saying that is for every 1 hydrogen, there's 1 oxygen. For every hydrogen, there's an oxygen. So this simplified version, that's an empirical formula. All right, we're going to do a few other examples. Another molecule, propene. If you could see propene, this is what it looks like. This is the actual makeup of it. The gray guys are, or the black guys, I guess, are the carbons. There's 3 of them. So there's 3 of those. There's 3 carbons. That's the black guys. There are 6 hydrogens. The hydrogens are the white guys. There's 6 of those. So that's the actual makeup. There's 3 carbons and 6 hydrogens. There's really a total of 9 atoms in this thing. But if I wanted to reduce it down to give you the lowest ratio, what do you notice both of those numbers are divisible by? What are both 3 and 6 divisible by? We can divide them both by 3, right? And get a whole number. So if you divide them both by 3, you would end up with 3 divided by 3, 1. And then for the hydrogens, 6 divided by 3, that's 2. So that way of writing the formula where you simplify it is called the empirical formula. Basically, for every one carbon, there are two hydrogens. There's twice as many hydrogens. All right, let's do a couple more. Let's do a couple more. So let's flip the page here. All right, another molecule that's actually quite common in the world. It's called benzene. Now, benzene, this is actually a molecule that's actually really toxic. If you ever go down the gas station and you notice that there's a sign, it's on every gas pump, and it says there's chemicals here that are known to the state of California to cause cancer. So what is in gasoline that causes cancer? Well, it's benzene, actually. So benzene, it's a very minor component of gasoline, but it's in there, and this is what it looks like. Now again, if we count up the atoms, same colors. The black ones are the carbons, the white ones are the hydrogens. There's 6 of each. So there's 6 of each. So if I was to ask you, what are they divisible by? If I want to simplify down this formula, they're both divisible by 6, I guess, right? And if we divide them both by 6, I could say for every one carbon, there's one hydrogen. So that would be the lowest ratio. It's a 1-to-1 ratio, really. All right, let's do another couple here. Oh, glucose. What the heck is glucose? Glucose is the stuff that's flowing through your brain, your veins right now, and your brain, actually. It's the thing that gives you energy. It's like the sugar in your body. It's called glucose. If we look at the formula, man, it's made up of a bunch of atoms. 6 carbons, 12 hydrogens, and 6 oxygens. This is what it looks like. There's a whole lot of atoms in glucose. If I tell you the exact number, that's the molecular formula. If I just tell you the ratio, that is the empirical formula. Now, the way we get that ratio is we take both sides, or we take all the subscripts, and we figure out what we can divide them by. So when you see 6 and 12 and 6, what are 6 and 12 and 6 divisible by? You could divide all those numbers by what number if you want to simplify? Okay, they're all divisible by 6. So if you divide them all by 6, and we simplify that formula, you could say for every carbon, 6 divided by 6 is 1, right? There is twice as many hydrogens. 12 divided by 6 is 2. And 6 divided by 6, 1 oxygen. So that's the lowest ratio. For every carbon, there's twice as many hydrogens. For every carbon, there's the same amount of oxygens. All right, one last one for our one last example. For our last example for water. All right, for water, H2O. Now, let's just, oh yeah, here's a molecule of it, right? This is what water looks like. And you notice for every 2 hydrogens, there's like 1 oxygen. Now, what do you notice about this? What can you divide both of those numbers by? Is there anything you can divide them by to get them smaller, to make it a simpler ratio? I don't think so, right? Both of them, this is like the lowest ratio. They're both divisible by 1, I guess you could say that. But if you divided them both by 1, you would get the same number, right? You would get the same subscripts. So I wanted to point this out to you because it is certainly possible that the molecular formula and the empirical formula are going to be the same. They could be the same. Like the lowest ratio also happens to be the actual number of atoms. All right, so with that, that's the difference between an empirical and a molecular formula. Maybe we'll try one more. So we'll do a little pop-up one here. We'll see. Okay, hopefully you got that one right. And with that, that's the end of this part of the lecture. We'll move on, and in the next part, we're going to tell you how you calculate an empirical formula.